Welcome back to the video lecture EE-371 Electromagnetic Field Theory. In today's lecture, you will learn Maxwell equation for time varying electromagnetic fields. This is Dr. Husnul Wahab. In last 5 lectures, we have developed the Maxwell equations for time invariant cases, and those Maxwell equations are as under. That is Maxwell equations for electrostatic magnetostatic field in differential form are given by equation 1, 2, 3, and 4. Equation number 1 represent that work done around any closed path is always equal to 0. This is the representation of Kirchhoff voltage law in field theory. The second relation del cross H is equal to J, where H is magnetic field intensity, J is current density. So in this case, J may be a conduction current density, which is due to the uh, field in a conductor. In a conductor, there are a large number of free charges. So this type of current density does exist in case of free charges, which is equal to J equal to sigma E. And there is another current density which is also known as convection current density, which is due to the speed or velocity of the charge. So this is the representation of Ampere circuital law in differential form. Del cross represent the curl of a magnetic field, which you have already learned in last lecture, that what is curl? Curl produce circulation. This circulation does exist in the presence or in the absence of the current source. Now, in chapter number 4, we have developed the um, Gauss's law in differential form. That is when we write del dot. So del dot means the divergence of D field. Divergence is related to closed surface analysis, and when according to Gauss's law, the total flux passes through any closed surface is always balanced by the total charge enclosed by that closed surface. And the fourth equation represent the Gauss's law for magnetic field, as there exists no single magnetic charge in nature, so that's why the magnetic flux are never ever uh, originated or terminated on any single point. So this represent sinusoidal representation. E is measured in volt per meter. H magnetic field intensity, which is measured in ampere per meter. J is current density. It may be impressed current density, that is applied current density, or convection current density, or conduction current density. The unit of current density is ampere per square meter. D is related to E through the permittivity of insulating material or any other material, and its unit is coulomb per square meter. B is related to, that is magnetic flux density is related to magnetic field intensity through the permeability of magnetic material, and its unit is Tesla. The Tesla or its unit is Weber per square meter, where Weber is the product equal to the product of Henry into ampere. Okay, so this is the representation of all four Maxwell equations in electrostatic case. Now the question is how to write these equations, represent these equations in integral form. But before that, I am going to show you that how to write these four Maxwell equations, how to expand these four Maxwell equations in rectangular coordinate system. So let us first consider the first equation, that del cross E. So we can expand this del cross E in rectangular coordinate system using determinant method. Let us assume that we have variation along each axis, along x-axis, y-axis, z-axis, and we have three components of electric field along each axis. So then how to expand del cross E? So ignore first column and first row, then the product of partial by partial y and ez minus partial by partial z into ey gave the x component of del cross E, the curl of E. Similarly, ignore the second column and first row, and then multiply partial by partial z with ex and partial by partial x with ez, give us the y component of the curl of electric field. Then in order to define the z component, so ignore the third column and first row, and then multiply partial by partial x with ey component of electric field minus partial by partial y with ex component, define the z component. So this whole relation is equal to 0. This is how to expand the first equation in rectangular coordinate system. You can also you can also expand the same equation in other coordinate system. You can find those information in the book. Now let us expand del cross H is equal to J, that is Ampere circuital law for magnetostatic case, that is for steady magnetic field. Let us assume that each field has three components along each axis, and J has three components along each axis, that is x-axis, y-axis, and z-axis. Then expand the left side of this equation according to the determinant of the curl of any vector field, which we have already done in first, in expanding the first relation. So according to the this relation, replace ez, ey, ex, ez, ey, and ex in this relation by hy, hz, hx, and then equate the same component on both sides of this equation. You can easily write down this equation in rectangular coordinate system. So in this way you can define the component of current density along each axis, that is jx, the x component of current density. So this is perpendicular to the plane containing uh, hz component and y component. It means jx is perpendicular to yz plane, because in that plane we have variation, a small variation along y-axis and z-axis. Similarly, you can obtain the y component, that is variation in x, z, and x plane, give another vector component that is in y direction. That is the variation of x with respect to z, hx component with respect to z, and the variation of hz component with respect to x, produce a third vector component which is directed along y-axis. So this vector is in the normal direction to the plane y is zx. Similarly, you can obtain the normal component along z-axis by varying the component, magnetic component, hy component, hx component in xy plane. So in this way you can expand the ampere circuital law for electrostatic field in a rectangular coordinate system. As we know that the del operator is given in this format in rectangular coordinate system that represent the variation along each axis, along x-axis, y-axis and z-axis. So let us assume that D field has three components, that is a component along x-axis, y-axis and z-axis. Then we can write the di divergence of D field in this form, that is partial by partial x dx, because the product dot product of same unit vector produce one, and the dot product of unequal or different unit vector produce zero result. So that's why this equation may be written in this form: partial by partial x dx plus partial by partial y dy plus partial by partial z dz equal to rho v, where rho v is the volume charge density. As I told you that there exists no single monopole in nature, so that's why del dot B, or the divergence of magnetic flux density, is always equal to zero. That is, magnetic flux neither terminated nor originated. So this produces sinusoidal effect, uh, solenoidal effect. So how to expand this equation in rectangular coordinate system? Write down del operator in rectangular coordinate system and assume that B has three components along each axis, that is along x-axis, y-axis and z-axis. Then take the dot product. So finally you will come across this relation, that is partial by partial x bx plus partial by partial y by plus partial by partial z bz. This is how to write the four Maxwell's equations for electrostatic magnetostatic field in rectangular coordinate system. You can also write down these equations in other curvilinear rectangular curvilinear coordinate system. uh, you can find those information in the book. That is how to expand these equation in a cylindrical coordinate system and spherical coordinate system. Now the question is how to write the above four equations, all these four equations in integral form. So in order to transform these equation from differential form to integral form, we use two basic theorem, that is Stokes theorem and divergence theorem. We apply the concept of Stokes theorem to open surface that is bounded by some contour C. So let us assume that an open surface is bounded by contour C. Then divide the open surface into a large number of incremental surfaces. Let us check the circulation effect at a single incremental surface, this one. So this one. Okay, so when we place this surface in a magnetic field or any field, so there produce the components of that field around the contour of an incremental surface. So if we assume the contribution of adjacent square, so the two components which are opposite to each other, they cancel the effect of each other. Similarly, when we consider the contribution of all squares in or all incremental surfaces, so eventually we come across the 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 boundary of this surface, that is contour, a contour that bound this open surface. So the same effect then does exist at the contour. So this means that whatever the effect exists at the contour, the same effect does exist over the open surface. So this is known as Stokes theorem. According to Stokes theorem, we can convert a contour integration of any vector field. A vector field is that vector which satisfy both divergence as well as the curl. So that is known as a vector field. So you can convert the contour integration by open surface integration of the curl of that vector, uh, such that the vector which is produced by del cross A is in normal direction to the incremental surface. So you can easily switch from surface integration to contour integration and contour integration to surface integration. Divergence theorem, whenever we deal with electromagnetic phenomenon in any uh, volume, when we do volume analysis, so in that case then we use divergence theorem. So in divergence theorem we assume that a volume, let us suppose that the volume is surrounded by a closed surface, then divide the volume into incremental volume, and let us assume that each volume contains some charge distribution. So the electric, let us consider this unit cell. So in this unit cell, let's say the electric lines of forces are originated in all direction, in upward direction, in left and right and bottom direction. So when we consider the contribution of adjacent incremental volume, so they cancel the effect of each other. And finally, when we consider the contribution of all incremental volume elements, so finally we come across the open surface, the closed surface. So the same effect which does exist inside the volume, one can find the same effect at the closed surface. So this means that we can replace the closed surface by volume surface integration, sorry, the closed surface integration by volume integration. That is, the closed surface integration of any vector field can be replaced by the volume integration of the divergence of that vector field. So you can, whenever you deal with the electromagnetic phenomenon in any volume, or you when you want to do volumetric analysis, then in that case we use divergence theorem to switch from closed surface integration to volume integration of the divergence of that vector field, or from volume integration of the divergence of that vector field to the surface integration of that vector field. So using these two theorems, now we are going to transform the differential form of Maxwell equation for electrostatic field into integral form. So let us first consider the equation number 1 and apply open. Actually the curl exists over the open surface, so apply open surface integration to equation number 1 on both sides, and then apply the Stokes theorem. So according to Stokes theorem we can replace the integration on the left side of this relation from surface integration to contour integration. That is, the contour integration of electric field around any closed path is equal to 0. So this is actually the representation of the Kirchhoff voltage law in field theory, which we have now denoted by equation number 1 prime. So this is the integral representation of first Maxwell equation. Later you will see that how to modify this equation for time varying field. Now let us consider the Ampere circuital law of for electrostatic field. So first apply the surface integration to equation number 2 on both sides, and then apply the Stokes theorem to the left side. We can replace the surface integration of the curl of magnetic field into contour integration of the magnetic field. So equation number 2 prime represent the integral form of Ampere circuital law. Then let us convert the Gauss's law for electrostatic field. So apply volume integration on both sides to equation number 3, and then use the divergence theorem. According to divergence theorem, we can replace the volume integration of the divergence of any vector field by surface integration, closed surface integration of that field. So the equation on the right side represent the integral form of Gauss's law for electrostatic field. In this case, there is no variation in the field with respect to time, whether it is field or whether it is field or the source. So there is no variation in the field with respect to time and in the source with respect to time. Similarly, apply the volume integration to the fourth equation and then apply the divergence theorem. So then you can write the fourth differential equation in integral form, that is b dot ds surface is equal to 0. That is, this equation actually represents that there exists no single charge as in case of electrostatic field, where we have positive or negative charge which we can easily separate from each other. But in this case we cannot separate the north pole from south pole, south pole from the north pole. So that's why there exists no single magnetic charge in nature. So that is, the closed surface integration of the magnetic flux density is always equal to 0. So this is how to write the Maxwell equation for electrostatic magnetostatic field in differential form and in integral form. Now we are going to modify the electrostatic Maxwell equations for time varying case. As in case of electrostatic field, del cross E is equal to 0. That is, the curl of magnetic field equal to 0, or the work done around any closed path is always equal to 0, because the electrostatic field is conservative field. So we can actually produce electromotive force in three different ways. Let us consider the figure. In the figure we have shown uh, a north and south pole, and there is a loop having voltmeter, galvanometer. So by moving the circuit, the rectangular circuit, in between north pole and south pole with respect to time, so there is we can induce EMF in the closed loop, or by changing the position of north and south pole in horizontal direction, we can induce EMF in the wire and the circuit. Similarly, in third method, if we move both the magnet as well as the circuit, so in that way we can induce EMF in the closed loop or closed path having galvanometer. The galvanometer detect the current that gave deflection whenever current passes through the galvanometer or voltmeter. So by either moving, changing the position of circuit in permanent magnet between north and south pole, we can induce EMF in the closed circuit, or by moving, by keeping the circuit in static condition, static state, and by changing the position of the north south pole, we can induce EMF in the closed loop, or by changing the position of the circuit, the closed loop, and the permanent magnet, we can induce EMF in the circuit. So this thing induced, so by by keeping any closed loop, a circuit in a time varying field, they induce EMF around the wire. So in this way, the electrostatic relation del cross E equal to 0 is modified by this auxiliary source, that is partial by partial TB, and there is a negative sign. This is because of Lenz's law. So del cross E equal to minus partial by partial TB represent Faraday's law of electromagnetic induction, where E is a function of position vector and time. Similarly, B field, magnetic flux density, now is a function of position vector and time. So this is how to write Faraday's law of electromagnetic induction in differential form. So by including this auxiliary source partial by partial TB, we can modify the del cross E equal to 0 relation for electrostatic field to time varying fields. Now let us how to write the Faraday's law of electromagnetic induction in integral form. So apply surface integration to this equation on both sides, and then use the Stokes theorem. So the Stokes theorem replace the open surface integration of the curl of E field to the contour integration of E field is equal to minus partial by partial T surface integration B dot ds. So this is how to write the Faraday's law of electromagnetic induction in integral form. As you know from previous lecture, that electromotive force is basically equal to, that is voltage difference or potential difference is equal to the contour integration E dot dl, and the total flux passes through any closed surface or open surface is given by this relation. So in the previous relation, equation number 1 prime, we can replace equation number 1 prime by this one, that is EMF is equal to minus partial by partial T phi. Now let us assume that the magnetic flux density is exponentially increasing in a cylindrical region defined by rho is less than b in z direction, and the magnetic flux density is exponentially increasing with respect to time. So how to use equation number 1 prime to obtain the electric field in terms of magnetic flux density? So look at, uh, consider rho equal to a path, the internal conductor of cylindrical shape. As we know that how to write dl in a cylindrical coordinate system. So by virtue of symmetry, there is no variation in phi component of electric field in between rho equal to a and rho equal to b. So we can easily write down this above relation in E phi a phi unit vector dot a phi a, let's say over the surface rho equal to a. So dl becomes equal to rho times d phi, which is equal to a times d phi. So by the dot product of a phi unit vector with a phi unit vector equal to 1. So from this equation we obtained that electromotive force around the around the closed contour or over the parameter of internal conductor becomes equal to E phi times 2 pi a. That is equation number A. Now how to find the total magnetic flux? So for that purpose we can use the open surface integration B dot ds, and as you know that in that the B field is increasing. According to this relation, the B field is exponentially increasing in z direction. So ds in this case would equal to az unit vector times rho d phi. So replace ds by this relation and plug in the uh, relation given in this example in this integration, and evaluate this integration. Eventually we come across equation number b. So now according to this relation, differentiate equation number b with respect to t and then simplify this relation. So the electric field in phi direction is equal to minus 1 upon 2 k naught b naught. B naught represent the maximum intensity of the magnetic flux density e power kTA. In journal, we can write E field in phi direction in this form. Replace A by rho. So this represent the total electric field in between rho equal to A and rho equal to B. Similar relation of electric field can also be obtained by using the differential form of Faraday's law, that is del cross E equal to minus partial by partial TB. So in this case, expand this relation in a cylindrical coordinate system, and then consider only the phi component of E field, and on the right side differentiate B, the given B field magnetic flux density, which is exponentially increasing with respect to time in z direction, then integrate both sides, so you will get what the same result as we got this result using this relation. EMF are the integral form of Faraday's law of electromagnetic induction. This one using equation number 1 prime. You can also obtain the same result using the differential form of Faraday's law. Now let us uh, solve a drill problem D9.1. Within a certain region, the permittivity of the electric material is 10 power minus 11 farad per meter. Permeability is 10 power minus 5 Henry per meter. We have also given the magnetic flux density component along x direction. So we have asked to use this equation, the Maxwell equations, and find electric field. So look at first expand del cross E and rectangular coordinate system, and in the present case we have given only the x component of magnetic flux density. So from this component you can easily define the x component of magnetic field, that is B is actually related to H through the permeability of magnetic material. So divide this relation by mu, so we can then write the x component of magnetic field, which is equal to 2 into 10 power minus 4 divided by mu cosine 10 power 5 t sine into 10 power minus 3 y. The unit of magnetic field intensity is ampere per meter, and the unit of magnetic flux density is Tesla or Weber per square meter. Expand the left side of this equation in rectangular coordinate system. In this case we have only one component of magnetic field, and uh, the H field depends on times as well as on y, single variable in rectangular coordinate system. So that is why we have replaced partial by partial x by 0 and partial by partial z by 0. So expand this del cross h in rectangular coordinate system and then simplify. We got del cross h equal to minus az partial by partial y hx. So differentiate the given function, the x component of magnetic field with respect to y. So and then divide the whole relation by epsilon, and then integrate both sides of this equation with respect to time. So that result in the easy component of electric field, that is E field minus, and using the given value of mu and epsilon, so we come across this relation. Similarly, in part B we have asked to find the total magnetic flux passes through the surface x equal to 0 and y varying from 0 to 40 meter and z varying from 0 to 2 meter and t is equal to 1 microsecond. So for these values and for given magnetic flux density component along x-axis, integrate this relation with respect to y and with respect to z at t equal to 1 microsecond for an x equal to 0 plane. So the evaluate this integration, this one, and finally we come across this relation. We come across this numerical value, that is phi equal to 0.3996 milliweber, and the C part of the same problem, we have asked to evaluate the contour integration of elect, electric field. So the obtained electric field has only one component, that is along z axis. So we have to select dl in z direction and then integrate this at y equal to 0 and y equal to 40 meter. The simplification of this integration give us minus 139.1304 volt. Now let us how to modify del cross H equal to J. So this form of Ampere's law is can easily be used in case of electrostatic field, but this form of Ampere's law doesn't doesn't obey the continuity relation. So look at the continuity relation is given by this relation, that is del dot j equal to minus partial by partial t rho v. This is also known as the law of conservation of charge. So apply divergence on both sides to this equation, and as we know that the divergence of curl is always equal to 0, so this means del dot j equal to 0. So this means that Ampere's law in this form is not inconsistent, is not consistent with the continuity relation. We must modify this relation to make it consistent with law of conservation of charge or continuity relation. So let us add an additional term g vector, and again apply divergence on both sides. So as we know that the divergence of curl is always equal to 0. Now using the continuity relation, according to continuity relation del dot j equal to minus partial by partial t rho v. So by replacing del dot j by minus partial by partial t rho v plus del dot j, and as we know that del dot d equal to rho v, so rearrange this equation, this one. So finally we come across that g equal to partial d by partial t. This term is known as the displacement current density. That is, for example, in a certain loop we include a capacitor, so still the current in the outer terminal is continuous. So that is because of this displacement current density. So Maxwell actually include this term with the Ampere's law and make it consistent with law of conservation of charge. So this is the representation of Ampere's law for time varying field, where J contain information about the applied current density, the convection current density, the conduction current density, and partial by partial TD represent the displacement current density, and its unit is ampere per square meter. So now the Ampere's law in this form is consistent with the law of conservation of charge or the continuity relation. So the remaining two relation, that is the divergence of D field and B field, remains the same in for both time invariant case and time varying case. Now how to write the Maxwell equations for time varying electromagnetic field? So in integral form, The Faraday's law can be expressed as the contour integration of E field E dot dl is equal to minus partial by partial T open surface integration of B dot ds. In differential form, using the Stokes theorem, you can replace this integral form of Faraday's of electromagnetic induction per time varying field to differential form. Usually in the laboratory we need the differential form of Maxwell equation, so that's why we replace the integral form of Maxwell equation into differential form. Similarly, the Ampere's law, the second equation represents the Ampere's law, that is contour integration h dot dl is equal to open surface integration j dot ds, which represent the total current, plus partial by partial T open surface integration d dot ds represent the displacement current. So you can replace this equation by differential equation. In differential equation, you can write the Ampere's law in this form, and the remaining two relation, that is Gauss's law for electrostatic electric field and Gauss's law for magnetic field. So using divergence theorem, you can write equation number 3 prime, which represent the differential form of Gauss's law for electric field, and equation number 4, the Gauss's law for magnetic field, and del dot B is equal to 0. This shows that there exists no magnetic charge in nature, so single magnetic charge in nature, so that's why del dot B is equal to 0. So that's all. Thank you. Please memorize these relations, how to write the Maxwell equations for electrostatic and magnetostatic field, and then how to modify those Maxwell's equations for time varying case, and how to write the Maxwell equation in integral form and differential form, and also solve some numerical problem to deeply understand the the concept of these Maxwell equations. Thank you.